University of Massachusetts at Amherst, the course on polymer rheology, chemical engineering, polymer science, 757, Professor H. Henning Winter, lecture 1A. The course will be twice a week. We will meet Mondays and Wednesdays for an hour and 15 minutes. I hope you got the general course announcement, which I have in front of me. We will maybe go through a few details. There will be 2 midterms in this class and an oral final exam. That will be a presentation by you about a subject which you will be picking, maybe suggesting to me. When we are through the class, about 2/3, you will maybe suggest a topic. We will go into details, and then you can decide what you like to work on. Now, the grading we should talk about is based on the midterm, 25% each, and 50% then is the final, comes from your paper. The general interest in polymer engineering, if you, I would need a focus here on the table in front of me. Yes, can you see that? Maybe I should move it more in the middle. Could you maybe, yes, magnify this a little. Make this, yes, very good, yeah. Yeah, I wanted to talk about why rheology is important in polymer engineering. And one reason is that during the lifetime of a polymer, which starts with the design of the molecule, maybe on a screen or so, and the synthesis, followed by the scale-up in a polymerization reactor, and then the compounding in big extruders or big machines, and followed by processing and end-use properties. In all those steps, rheology is very helpful as a tool. For instance, if we look at the molecular design, say a chemist looking at different molecular architectures, likes to work with a rheologist because small changes in molecular architecture have a large effect on the rheological response. It's a very sensitive physical technique to see differences. You still wouldn't know what the difference is. You would just see some changes in the rheological behavior, but where it comes from is another question. But you would see phase transitions very nicely in a rheological experiments, phase transitions in a blend, or phase transition for crystallization, or phase separation of a block copolymer, for instance, is very nicely seen in a rheological experiment. And then when working closely with the chemist, you can tailor those transitions, move to different transition temperatures. So that's very powerful. The polymerization then and the compounding should be somehow in connection with rheology, because rheology would be a good sensor to see small changes in the molecule. When you might get higher molecular weight or more branching or less, or whatever, you have to coordinate that. And one of the most sensitive indicators is maybe the relaxation time spectrum or the viscosity of the polymeric material, sometimes more sensitive than DSC or other physical techniques. So rheology as a sensor is very powerful. And then during processing, towards the end here, you would like to predict the forces in a processing equipment, the flow rates. And rheology helps you to do that. You would write down a model of polymer processing in this case. And then, of course, the end-use properties are often mechanical properties which are deciding, and mechanical properties are described within the framework of rheology. So it has different aspects in all those states of a life of a polymeric molecule. For processing, for instance, let me show you an example here. What tools would we need to describe polymer processing? I symbolized it very simply by the flow through a die. Here there would be a big reservoir of polymeric material, comes from an extruder. It's molten, well mixed, ready to be shaped into some extrudate. So we would like to know what's the state of stress of this polymeric material, this material element here. And to quantify this, we would need lots of information. We, for instance, would need the constitutive equation. That means the stress as a function of the strain history of this material, and of the strain history, and as a function of the molecular mobility. Large molecules can rearrange faster. You can, the small molecules rearrange faster, and you cannot introduce much molecular orientation. Well, a large molecule of high molecular weight can be oriented in flow, and most likely this orientation will stay and will determine then the properties in the extrudate which is leaving this die. So we need a constitutive equation, and much of this course will be on the development of constitutive equations. In addition, we need a force balance on this material element, which is called the linear momentum balance. We would look at conservation of mass. There is conservation of mass has to be satisfied in all cases. In our case here with polymeric liquids, the density is constant in nearly all cases. If you don't go to very extreme situations of large temperature gradients or large pressure drops, then you can say that the divergence of the velocity is equal to 0. That's equivalent to saying that the density is constant. And processing is not at constant temperature. There are large temperature gradients. You're melting the material in an extruder, say, when you introduce the polymer, and then you mix it, and then afterwards, after shaping it, you cool it down. So there's always a transient temperature field, and that would be described by the conservation of energy. I will not talk much about conservation of energy in this case, but we certainly will talk about temperature effects within the rheological constitutification, so that you're able to describe that. Now, this would be our system of equations together with boundary conditions for the temperature and for the velocity. And that has to be solved in a complicated scheme. Most likely it will be a numerical scheme. And here I just want to demonstrate the complications. Blue lines connect the stress tensor wherever it appears. Stress appears in the constitutive equation, and it appears in the conservation of linear momentum. There we have the stress gradients and the pressure gradients, and sometimes gravity is coming in, or maybe acceleration. In our case, we mostly have low Reynolds number flows, so acceleration is not very important. So all those acceleration terms vanish on this side. So it's a simplified form of the linear momentum, conservation of linear momentum, which we are using. And down here in the conservation of energy, the stress appears because the mechanical energy which we enter into the flow system is converted into internal energy. And that's the phenomenon which you would experience when you take a metal paper clip and bend it back and forth. You're deforming a paper clip. And on the range where you're bending this paper clip, you will see that the paper clip is heating up. What you would do in that experiment is you would convert the energy which you put in by bending the paper clip into internal energy motion of molecules of the metal the paper clip is made of. And the same thing happens in polymeric materials. The stresses are often high. The rate of deformations are high. So there would be some temperature change due to that viscous dissipation term. And this term would be the energy per unit volume and unit time occurring in the system. Okay, so that's the blue term. Now the green lines here connect velocity wherever it occurs, and you can see that conservation of mass has a velocity term. And then the constitutive equation has a velocity term because the strain history is entering here. And in solving those equations, for instance, you need the strain history for the stress, and the stress is put into the conservation of linear momentum, and everything is coupled, and you have to invent some nice strategies to come to a solution. Fortunately, there are better and better numerical codes for solving this type of flow problem. And those are whole research groups following up in this area. But what those research groups need, really, are constitutive equations and a quantitative description of the flow behavior of the material. And that's what we are going to work on in this course. So in an overview here of the course objectives, there will be a short introduction into continuum mechanics. By the way, I will make a copy of all of those for you, so don't worry about this. Okay, I should have brought all this, but so I will give you all this material, and then you don't have to write it in. But if you have questions, maybe since you don't have to write, maybe you have some good ideas and you will ask some questions, and that's always welcome. So in the beginning of the course, we will talk about continuum mechanics principles. We have to have the same language. We'll define stress and strain and all those details, but it will be a very short introduction. And then the main part of this course will be on experimental observations. How do polymeric liquids behave? And we want to discuss techniques to study this behavior. We will look at the results of those experiments. They have to be analyzed. Somehow we need an abstraction then of those experiments. And that abstraction then will lead into constitutive equations, which can be used by people, for instance, who do the numerical modeling of processing flows. But it's not so easy to do an experiment in the rheology lab. You just deform a material, and then from this deformation you have some data to reduce that into a constitutive equation, which makes sense somewhat. But at the end of the course, I hope you will be able to do that. And then, after having built up these techniques, we will look at the rheology of some structured polymeric materials. And that's where our research interest is. We're looking at blends, block copolymers, liquid crystals. So rheology is a tool for us to look at those materials in greater detail. All the course will be on the continuum level. Sometimes we will talk about molecular arguments, molecular explanations of certain phenomena, but it's basically a continuum mechanics course where we use continuum tools like rheometry and modeling of flows. And the theory on this level is concerned about the equation for the stress, the constitutive equation, which relates stress with strain histories. The molecular level will be touched occasionally, but there are equally interesting experiments. For instance, birefringence could be measured, looking at the anisotropy of the molecule, the electrical anisotropy, or some NMR techniques are coming up which look at mobility of small segments of the chain. Or fluorescence tracers will give some information on molecular mobility, but maybe if we have a little bit of time at the end, we can talk about this. And theory has advanced significantly in recent years. The most popular models are really the reptation models in the moment, which have the following concept. In the reptation theory, one would look at a macromolecule, long chains, and not allow the penetration of one chain past the other. There's always a hindrance. A chain can only move past the other chain by a lateral motion, but it cannot go past the second chain. In older models, in the network model, the so-called phantom network theory, all the forces are assigned to the cross-linking points, to the nodal points, and the chains are allowed to move freely around. And this is a completely different picture, and probably the more realistic picture comes out of the raptation model with respect to Dijen, in Doi, and Edwards. Classical models like Gauss and Sim, I'm sure you heard parts of that in physical chemistry, so I won't go into detail. And I also will not go into detail here with the large-scale applications like extrusion or injection molding, or will not talk about large processing models. The general outline of the course goes something like this. We will first talk about rheological phenomena, and I will do this today. We will talk about those. We will discuss basic concepts to have the same notation for stress, strain, and for the conservation of linear momentum and of mass. And then we will look at specific flows. Somehow a general deformation is too complicated to be analyzed and to extract a material parameter from that. So we have to simplify somehow the approach. We have to look at the specific shear flow and the specific extensional flow and learn about the behavior from those flows, and then we can generalize into constitutive equations. And those equations then are applicable to arbitrary flows. But the learning process goes through those specific flows. We have to classify the flows and then measure look at some measurements in those specific cases. One example here is the steady shear viscosity. That's a very well-known property. It's dominated by shear thinning phenomenon, and it's the power law viscosity, all of this. So this comes in with the material functions. It's not a constitutive equation. It's just an observation, a stress-strain relation in a certain type of flow, in steady shear flow. But it's very helpful for the analysis of specific types of flows. We will look at material functions, and then we go through a few rheometer design details. They are interesting to analyze, interesting for getting an understanding of the material behavior. And then we will look at the relaxation time behavior. You will see in a moment what I mean with relaxation times. It's kind of the fingerprint of a polymeric material, the relaxation time spectrum. And we would like to quantify that for some simple materials and also for some complicated materials later on. And then we can go to some constitutive equations for large strains, and that's more complicated. Now, the prerequisites for this course are really only modest knowledge of vectors, tensor, and differential equations. There's not too much needed. Also, there's a very good appendix in the textbook. I will come to the book in a moment. And there is only an introductory knowledge in fluid mechanics necessary. Because our flows are they are so simple. We have just a simple shear flow and extensional flow. More complicated flows are too hard to work on. That's the basic reason why we will stay in the simple part of fluid mechanics. For the notation, we will use the SI units, the standard units. Metric system, for instance, the viscosity will be written down in Pascal seconds. The value is given in Pascal seconds, not in poise or poise, whatever you want to call this. But 10 poise are equal to 1 Pascal second. So as a reference, the viscosity of water at 20 degrees C is a millipascal second, 10 to the minus 3 Pascal second. While the viscosity, I just came back from Germany, so put in a German one. So the viscosity of a polymeric material is in the order of 10 to the 3 Pascal seconds, or 10 to the 4. And due to shear thinning, then, when you deform the material, that can decrease by 2 orders of magnitude. The sign convention for the stress will be the following. Tension is a positive stress in our case. So if whenever we have a force pulling on a surface, the force divided by surface area is the tension in this case, and it's positive if pulling, or it's negative if it's a pressure, if we are pushing. Bought a few books. There are many books in rheology, fortunately. In the last 15 years, lots of mystery has cleared up in rheology. Before that, there was more a question of intuition and wasn't as systematic. And a large contribution to this systematic approach, I think, came from Bird and from his school, his co-workers here, Armstrong and Hasaga. And that's why I picked this as a recommended book for this course. It has a very broad coverage of all the continuum mechanics fundamentals. It doesn't have molecular aspects. There's a second volume to this, and that has the molecular dynamics aspects of the Bird school. There are other schools like Dorian Edwards, and they also have a book on molecular dynamics. So, but since I see on the continuum level, I thought that this is a very broad coverage of this subject, and at least in the first part of the course, I will use this extensively when we go to block copolymers, blends, liquid crystals, so we have to take some additional literature to complement that. Very nice book is this book by Ron Larson, who, by the way, will give a seminar tomorrow here at 11 o'clock in chemical engineering. I like this book quite a bit. It's very concise. It's fairly small, and it nicely combines continuum mechanics aspects with molecular aspects. And in the end, it has a few special topic sections which give insight in novel developments. Now here's a book which is rare. It's not available anymore. It's the book by Lodge. It's called Elastic Liquids. We sometimes call polymeric liquids elastic liquids because of this treatise in 1964. Very nice continuum mechanics treatment, but also a transformation of the rubber theory of Treloar and this type of school towards the rubber-like liquid. You know, it's using the concept of elasticity in a macromolecular material and applying this to macromolecular liquid where the chains can relax, where they don't have a permanent elasticity. So that's very nice text. Linear viscoelasticity has still its Bible here in Ferry, I think, but there are some newer books. And by the way, I will give you a list of all kinds of books in rheology. I'm just picking a few ones which were very helpful. Ferry is just retired in University of Wisconsin, but it's amazing what he knows about molecules. I remember one meeting we had, and there was a heavy argument, and Ferry's proof that he was right and the other person was wrong. His proof was, I know my molecules. So he didn't explain it on first principles. It's just that he knows molecules, so he's right. And very often he is right. Now, this is a book by one of the pioneers in the field, Janicic Kriegel, in the field of birefringence. Very nice experimental work and analysis, and you will find lots of information about experimental setups, especially when you combine optical techniques with rheology. That's a very good book. There are some new review articles by Jerry Fuller out of Stanford, which are also helpful. But this is very nice. Now here's a recent book by Dealey and Wisburn, in which the two authors try to build a bridge from rheology to polymer processing applications. There's always this question, what is this good for? And it is not easy to apply rheology to polymer processing. And in this course, I'm very interested in this type of application. So in this course, I will try to be quantitative, describe the rheological behavior in terms of numbers so that you can apply rheology to those things. So far, the introduction. I would like to come to the real subject now. You see we have 50 minutes left. And this first subject is really rheological phenomena. In Bird, Armstrong, and Hasager, the first volume, we always use first volume, so I will, in the future, I will not write this down. You will find from 55 to page 98 a detailed description of a variety of rheological phenomena, some exciting experiments, very playful, very informative, often very complicated to analyze. The flow is so complex that you can see some basic features, but you would not be able to extract a quantitative information which you would be able to transfer then into a quantitative equation, for instance. But still, those phenomena are very illustrative. They kind of demonstrate the range of possibilities here. Larson has, in his first few pages, also a nice introduction on those phenomena. There are two movies, and I will try to get a hold of those. The first one is by Herschel Markowitz. It's quite old, this movie, but still, phenomena haven't changed. The rheological behavior of fluids, and then more recently, Ken Walters and Broadbent, non-Newtonian fluids, have very informative description of those phenomena. And then there are some classical papers. There is always the original work by Gizikos. And I still remember when I, as a student, visited Gizikos in his lab, and he showed his fantastic flow visualization experiments. This was at Bayer. Very, very informative and motivating people. Those nice experiments. So maybe I can get some data from him to show to you. To discuss the classical phenomena, to discuss rheological phenomena, I would like to come back to some classical phenomena which you might get used, or which you have seen before, which might look familiar, I hope. So very simply, let's consider a material element which is square at some initial time, and then due to a force, it's being deformed. It's sheared out, this material element. And the shearing motion is described by this angle alpha, which we are generating by this shearing motion. And the common way of describing this is the following. We would say the strain, gamma, in this case, is equal to tangent alpha. So that's this angle is really giving us describing the strain. And the stress on the surface area is equal to the force F divided by the surface area. That's the shear stress. On the bottom of that material element, there's an equal and opposite shear stress. And later on, when we talk about the stress tensor, you will see that even on the sides, the symmetry of the stress tensor will require that there is a shear stress on the sides. And that's not obvious to see. That has to be proven. But in the moment, we were just deforming this material element. And the question is, what's the response? What's the stress response of this material element in cases of, say, a solid? If we look at classical elasticity, looking at the Hookean solid, we would have a material which has some large-scale connectivity, maybe a crystal, or some piece of rubber, or some glassy. See, the deformation is large or small depending on the conditions, on the stiffness of this material. But the stress response now, in this case, is just proportional to the strain, to the shear strain, and the coefficient describing that is the modulus, the so-called shear modulus. And if you would perform a similar experiment in extension, you would get an extensional modulus, and there's a one-to-one correlation between the shear modulus and the extensional modulus. It's factor 3 in case of constant density. Otherwise, you would have to describe density changes. But let's neglect density changes in the moment here. So for the Hookean solid, for the material of classical elasticity, only one material parameter describes the behavior, and that's the modulus. That's all we need. That's the whole, that's all. And gamma is the shear strain. That's the same which was defined up here. Just repeated it to make clear. And the dimension is the dimensionless, the shear strain, and the modulus has the dimension of Pascal. Pascal is Newton per square meter. For a second material group now, a second ideal material group, that of classical fluid mechanics, those are the Newtonian fluids, we would look at materials of low molecular weight. But it cannot be a solid of low molecular weight. It has to be a liquid, it has to be molten, or it has to be in the state of gas. The molecules of the liquid are highly mobile. They are flowing. They are just, when you have the liquid in a container, then it's just filling the container. And the liquid is filling the container, the lower part of the container. And to come back to the solid has a characteristic shape. You don't have to contain it in something else. When you deform a solid, you change it, you generate a new shape for the solid, and when you let go, it goes back into its natural shape. So solid always has its natural shape, and the liquid has no character, if you wish. It just adopts whatever the surrounding prescribes it to be. Now, the response in the liquid is given by the shear rate, not by the angle, but by the rate of change of this angle. If you change that angle fast, you have a high stress. If you change it slowly, you have a low stress. And the coefficient of proportionality is called viscosity. It has dimension of Pascal seconds. The shear rate is the time derivative of the shear strain, and it's given in seconds to the -1. That's the dimension. Okay, so far that's classical behavior. That's just as a reference. And now let's go to the polymeric materials, the polymeric liquid, better to be more precise. And those materials have an intermediate behavior between liquid and solid. And that makes them really interesting to us. Those materials are called viscoelastic. We say they're it's viscoelasticity phenomena, or when you look at maybe Ferry's book, it's the whole book on linear viscoelasticity. We have to specify what this is in a moment. But basically, the behavior between the ideal Hookean and the ideal Newtonian behavior, this viscoelastic behavior, has an interesting origin, and in a hand-waving type argument, you can describe the origin of the elasticity of those materials. And the molecules here, they are of high molecular, so you have very large molecules, macromolecules, and those macromolecules give rise to the viscoelastic behavior, and that's what we will be focusing on. But there are other materials which have some large-scale connectivity. You might have a suspension where particles form some bridges and have some large structure which can be broken in flow or can be built up even in flow. Some materials have to be deformed to get some connectivity. So there's a breakup, or in some cases, a buildup of structure during flow. And this can be seen in suspensions, especially. For all the other materials, here, colloids, block copolymers, liquid crystals, the flow mostly breaks down the structure, and the connectivity or elastic behavior is reduced. Ionomers sometimes become more connected when you deform them. Somehow molecules are clumped together, and when you deform them, you stretch them out, and then they are able to connect into neighboring molecules, and you form some large-scale connectivity. So for ionomers, a building up of structure might very well occur occur during flow. So those phenomena give rise to the viscoelastic behavior. And should we break now, or let me see whether they. And should we break now, or yeah? Okay, let's have a quick break. Yeah, he has to change the tape, and then we will continue. University of Massachusetts at Amherst, Chemical Engineering, Polymer Science 757, Polymer Rheology, Professor H.H. Winter, Lecture 1B. I want to discuss two basic concepts with you, and let's do this on the blackboard. And so two basic concepts, and the first one is the material characteristic time. And we will define a dimensionless group, which is called the Deborah number. The second concept to look at is elasticity. Should state capital letters here. Elasticity is normally associated with a solid material, with rubber or so. But we will talk about elasticity of polymeric liquids. And this will give rise to some normal stresses. And it will give rise to recovery. Some expressions which I have to define by using some experiments. So the first concept to talk about is that of the characteristic time, and in that connection, the definition of the Deborah number. Which is described by the symbol dE. And for that purpose, I would like to do an experiment here with you. I brought this material here of, it's a polymeric liquid. At room temperature, it flows. You can see that it was spreading out here on the substrate, was taking the shape of its surrounding, typical property of a liquid. And if you wait long enough, it would really spread out in this beaker. And when I subject it to a constant load, I can deform that. A constant, steady load allows me to shape this material as you could shape a piece of clay. Now, this is under steady load. And let me write this down here. If you have steady load, you're generating flow, and it's a type of a liquid behavior which we are observing. In the case of a impulse type of deformation, I can bounce it on the floor here. See? It's deforming when it hits the floor, but it recovers its old shape. And that's a typical behavior for a solid material. So depending on our experimental condition here, now it behaves like a liquid and it flows. Or if we have an impulse load, it has a solid response. In the sense that it has its natural shape, and it always goes back into that shape to release its stress. It will be under stress when it hits the surface, and then it goes stress-free, and it goes back to its old shape. Typical solid behavior. Now, let's be a little more specific and talk about an experiment. We would like to translate this now. In the laboratory, we wouldn't want to throw around a bouncing putty and measure forces on that. We would do something similar. So we translate this into a well-defined experiment. Well-defined experiment. And this experiment would require a periodic load. Say we would deform the material. We would deform the material periodically with a shear strain gamma as a function of time. Remember, gamma was in our for our little material element was given by the tangent of angle alpha. So gamma gave the deformation. So if we have now gamma plotted as a function of time, and we are deforming the material periodically, we always go back to the zero position, then we have a negative deformation, and then positive, and then we are alternating the deformation. A period of this experiment is given by 2 pi divided by the frequency of this experiment, and that's our parameter. We can deform the material at very high rates or low rates. We can bounce it at a very high frequency, and then we have something like this, or we can operate at low frequency, and we have liquid behavior. So let's write this down. Low frequency, where, say, a characteristic time of this material times the frequency of the experiment is very, very small. And in this case, the material behavior is described by liquid property, and this is liquid with viscosity. And this is the material property which is describing that. Or if we bounce this our sample here at high frequency, say lambda omega is much, much larger than 1, then we find that the material behaves like a solid with modulus G. And again, there's this one property typical for that behavior. And lambda, in this case, is defined as the ratio of the viscosity divided by the modulus. And this is called the relaxation time. Okay? And you could define the Deborah number for this experiment. That's the objective of this whole derivation by a group like this. And the Deborah number is given by the ratio of the relaxation time to the characteristic process time. And what is that in our case? The relaxation time, say, is lambda, given as the material property. And what's the process time, a characteristic process time for our experiment? It's the duration of this bouncing experiment, the period. So this is given as 2 pi divided by omega, or we would say that lambda omega divided by 2 pi is the Deborah number. This is the Deborah number of this experiment. The material has a characteristic time, and that's related to the experimental time. And if this ratio is very large, if lambda omega is very large, the material behaves like a solid. And if this is very small, then this material behaves like a liquid. And if the Deborah number, the value of the Deborah number is intermediate, and I drew this here in a more general form, if you please switch camera here onto this. Here, this is the definition of the Deborah number. In our experiment, then if the Deborah number is in the order of 1, then the material behaves viscoelastic, behaves between the characteristic solid or the characteristic liquid, or the ideal solid or ideal liquid. That's this intermediate behavior. And that's where the viscoelastic properties come into play. And for the process time now depends on your specific experiment. And in this example, the process time was given by the period here of the bouncing of the material. So that was the first concept which I want to introduce. So the material is, you cannot say the material is elastic or the material is viscous by itself. You always have to say, under which conditions? You say, under those conditions, the material is elastic. In other conditions, it's viscous. And the characteristic parameter which allows you to distinguish between those is the Deborah number. It's the most important dimensionless group for applications in rheology. Okay? So under some conditions, the material behaves elastic. And where does this elasticity comes in? Let's talk more about the elasticity of this material. And there are some hand-waving arguments, molecular arguments to describe that. It's very hard to predict the elastic behavior from first principles. But still, roughly, the understanding is there. We would say that the macromolecules assume a state of maximum disorder. Brownian motion will generate a coiled formation for this macromolecule, for this long chain. And the molecules are penetrating each other. You don't have just a single coil here and a single coil next to each other. Those coils are interpenetrating, and somehow it doesn't matter whether you are talking about polymer solution, where this macromolecule is swollen by a solvent, and it's fairly big and randomly coiled, or whether the macromolecules is in the vicinity of other macromolecules which also swell the original coil. So they're penetrating each other, and in Brownian motion they only can pass each other, but they cannot. The chains cannot cross each other. That's a physical constraint. Now, during flow, those macromolecules are extended, and they are moved into a state of higher order because of this extending. You have more chains in direction of your extension than chains sideways. So there's a higher order introduced, and this higher order, together with Brownian motion, gives rise to a retraction force in this molecule. The molecule wants to go back to this disordered coiled state, and the sum of all those retraction forces on the molecules give rise to a macroscopic stress. And in flow, this will give rise to some normal stresses, and in the same way also in extensional flow. Doesn't matter. There are some interesting stresses, and we will talk about those when we look at the real phenomena in a moment. Now, when the flow is being stopped, then the molecules retract, and then they go back to their coiled state. And the time needed for the molecules to go back to their coiled state, you form the material, you stop it, and then it goes back. That time is exactly the characteristic time, the longest time of the macromolecule. That's what we are seeing. That's the so-called relaxation time. Now, a molecule does not only retract in its entity, there are also rearrangement of small segments or parts of this macromolecule. And those rearrangements are given by shorter relaxation times. Somehow, this would be the longest relaxation time, which is associated with the entire rearrangement, the rearrangement of the whole molecule. But small-scale rearrangement gives rise to shorter and shorter relaxation times. So the relaxation behavior will be given here by a spectrum of relaxation times which are in the order between 0, very short, and the maximum relaxation time, which is characteristic for the entire molecule to go back to its original shape. So that's the molecular picture, and we can draw a molecule, for instance, in shear flow. The coiled molecule is not a sphere. That it is somehow an ellipsoid, but it basically has an aspect ratio close to 1 in all directions. So if this molecule here on the left side is the original, the molecule at rest, then a shear flow, a shearing of that macromolecule, will result in a distortion. It will be elongated. There are more strands along in this direction. There's an order in this material. And this molecule tries to retract in this case. And there will be a tension in this molecule. So for producing this flow, we are shearing in this way. But the molecules, now they want to go back to their random state, and they will give rise to a tension in this direction. And this tension then has a projection in this direction. There's a tension in direction of our shear flow, which is quite amazing. People discovered that. I think Weissenberg discovered that in the 30s. He sheared a material, applied a shear stress, and he found that there's a tension along the direction of flow, tension in the material in the direction of flow. And that's quite surprising. It gives rise to some interesting phenomena. Now, quite normal in extensional flow. Let's say a molecule is part of a little piece of rubber which is being stretched here in this deformation. Then this molecule will be elongated, and it wants to retract also and gives rise to a stress. because it's ordered here and disordered in entropic stress contribution, which we're talking about. And that's quite normal. That's used in fiber spinning. You can spin fibers out of polymeric materials because they are supporting a stress of this type. It's a very nice property of a material. If you would take a low molecular weight strand, if you, let's say, take a silicone oil or a stream of water, when you pull on that, you will break it immediately. But a string like this will just orient more and get tougher, and you can spin it into elongated geometries. So that's a typical. That's a molecular picture. It's a typical phenomenon. Now let's see what. Let's do a few experiments. Or I don't have them here, but I have some pictures. For instance, let's take a beaker of material and stick in a rotor from the top here and start rotating. Now, if this is a Newtonian liquid, then you're just swirling the material around, and the centrifugal forces give rise to some pressure gradient to the outside. They are balanced by gravity, and you get a parabolic surface. You all know this when stirring coffee or so. You can see that type of phenomenon. You stir it, and then you take off your spoon, and you have your parabola. Now, in polymeric liquid, there's a shearing motion between the moving surface and the quiescent surface at the wall of the beaker. And by introducing that shearing motion, you introduce a stress in direction of the streamlines. Now, those streamlines are going in a circle around the rotor of that from this experiment. Now, it's like you can imagine a rubber band, a circular rubber band under tension, and lots of those rubber bands, and they want to shorten. And the whole material wants to shrink on top of the center here of the beaker. So they want to move to the center, and this gives rise to this rod climbing experiment. And the phenomenon is very, very strong. You don't need much elasticity to get this rod climbing phenomenon. There is Joseph in Minnesota is building a device of this type to measure the smallest beginning of elasticity in this case. It's so sensitive to show elasticity in polymeric materials. He says that's the most sensitive way of detecting elasticity in a material. In a molten polymer, if you have a polyethylene melt and you do this, it's a real dominating effect. It basically climbs and climbs until your beaker is empty. Now I brought some picture here. There was here Franz Nazem in Madison did some nice experiments. Here's the beaker. The Newtonian effect is not seen very drastically, but you can see the climbing, and it will continue climbing until there's no contact here, and then there's no shearing motion anymore, so there's the driving mechanism is lost in this experiment. But that's a typical phenomenon, and it's nasty if you want to mix something. If, let's say, you design a nice laboratory mixer for, I don't know, maybe you synthesize a new polymer, and then you try to mix it, and it's all coming up the stirrer, and you don't have any mixing motion. Now, if you prevent this climbing up, if you put a lid on that and you have a rotor going, then there are some interesting secondary flows developing. Those have been studied extensively by Giesecke, but maybe here, see there's a rotating disk, and then there's a swirling motion introduced. And I think here it's by, this is gravity, this Newtonian liquid goes one way, the rotating disk throws it to the outside, and the motion goes like this. And here, for the polymeric liquid, the rotating disk pulls it to the inside, and the motion is the opposite. In most cases, the elasticity-induced motion is opposite to the gravity-induced motion. Or here you have a sphere rotating, and then you get some interesting pattern. But very often, if you want to mix a liquid, that's not the pattern which you would like to have. You would have to break this pattern and change that just to take care of this elasticity. But it's beautiful also, so that's probably one reason why people study that so extensively. There are other instabilities coming in, typical Taylor-Couette instabilities, which are known for Newtonian liquids if you have a rotating cylinder in a stationary outer cylinder or vice versa. Then you have some zones which are rotating, and elasticity changes the onset of those and the direction of those vortices in the same way. Okay, now let's look at a different experiment. A very, very simple experiment, and you will be surprised how many observations you can make with that experiment. It's just the flow through a simple capillary. Let's assume you have a reservoir of fluid and a narrow capillary of length L, and you push liquid through here, which leaves the dye, and for the polymeric material, it will swell here. It's increasing its diameter. And there are three zones we can look at. One is the entrance zone. One is the zone of dye flow here, of constant cross-section, channel of constant cross-section. And the third zone is the free surface zone. Let's talk about the entrance flow first. There we would look at stretching. The velocity is low here and high there, so it's a stretching out of material elements. And then there's some interesting vortex formation. I will come back to this picture in a moment. Let's just look at the entrance region of that system. I don't know whether you can see that. This is also taken, I think those are pictures by Giesecke, but others did similar experiments. For Newtonian liquid, somehow, this is now not a gradual contraction, it's flow coming in from all sides into an orifice here, and this is linear, but then when you add a little bit of polymer, then the flow geometry changes completely. There's a small region where all the flow goes down into the orifice, and then there are vortices which are hindering basically the flow. You have to drive those vortices. And then when you increase the flow rate, when you go to higher rates, then those vortices start to move back and forth, or they might start to rotate, and you have all kinds of very very interesting instabilities. This actually might occur in a polymer melt. When you extrude a strand you produce some melt in an extruder, and you extrude it to make a rod, say. And you would want to increase your production. You go to higher and higher rates. And then you generate vortices like this, and they start to move around. And then when you extrudate, you will see that the history of this material elements is asymmetric, and then you might have a corkscrew coming out of the die. So there's always a limitation in production because of instabilities, and one instability might come from this inlet. From this inlet region. Now let's look at the zone in the die, the channel flow region. What's happening here? The most drastic phenomenon is shear thinning, and this goes something like this. You would mount some pressure transducers along the die, so you measure the pressure, say, in two positions, or you measure the pressure upstream, and you have zero pressure at the outlet of your die. So you measure the pressure drop, or the pressure which is necessary to generate that flow. And you also measure the average velocity, or the volume flow rate going through this die. So when you increase the pressure, you will have more flow. So for Newtonian liquid, the velocity increases. But for a polymeric liquid, it does not just increase linearly, it increases much faster. Or you could say the viscosity of the material goes down. At high rates of deformation, suddenly the viscosity is a tenth or a hundredth of its original viscosity. Viscosity is drastically reduced. And that's the so-called shear thinning phenomenon. The velocity distribution is also different. can you distinguish the red here is the more flat profile, that would be for polymeric materials, and the green one is a parabola of second order when you talk about a slit or a flow in a round capillary. Okay, shear thinning. Now how about transient? Here there are transient phenomena. The typical Deborah number would be, again, the characteristic time of the material divided by the residence time of the material when it goes through this capillary. And if this number is very small, then the material can relax. The relaxation time is short compared to the residence time, and elastic effects have little little influence on the flow in the die. But if this Deborah number is very large, then the material does not relax while it goes through this die, and it will clearly remember that upstream it was a big lump which was stretched for a short time here, but when it comes out here, it will swell again. So, okay? So by making this capillary longer, you could prevent this swelling effect. Okay? At least that's what I thought in the beginning. That's when it gets interesting. Now, and that's the interesting observation now. And let me jump to the free surface flow since I started talking about swelling. Even if this capillary is very, very long, so the material clearly doesn't remember that it was stretched when it entered the capillary, even then, the material swells at the exit. It swells. And the diameter is 2 or 2.5 or 3 times as big as the diameter of the capillary. It's a very large phenomenon. And that's due, again, to the normal stresses. Remember, in shear flow, we had a shear deformation of the material element. Let me maybe draw this, go back to this picture here. Here in shear flow, we deformed our molecule, and then we have some tension along the streamline. Okay? And now we are extruding a material which comes out of the die, and there's tension on it, and it snaps back. And it gives rise to swelling, even if the die is very, very long. I will show, let me show you some pictures on this. This is, for instance, those are pictures on exudate swell. This is taken from Arthur Lodge's book. I mean, like this. His photograph didn't come out in my, here. This is better. See, this is a Newtonian liquid which is extruded from a capillary, and this is a polymer solution. A few macromolecules are in there, and it's not very concentrated. A few macromolecules, and it swells, and the swelling is very, very large. When you draw this here for the polymer, between 2 or 3 times the capillary diameter can be seen in the exudate. On the Newtonian liquid, it shrinks. Now, in the Newtonian liquid, everything is given by a balance, by basically this. The dominating thing is conservation of kinetic energy. You have a parabolic profile in the capillary. You have a flat velocity profile outside in the free surface. And when you integrate those profiles to get the kinetic energy inside and outside, then you can see that the strand will have to shrink to satisfy at least the intermediate Reynolds numbers where inertia is important. But here, the normal stresses are really dominating. Either normal stresses because of the entrance flow into the capillary, or if the capillary is long, normal stresses due to shear flow. Now, Tanner analyzed this problem here. He calculated the swelling, he calculated this value, and he found, using a very simple model, it's amazing how nice it is in spite of all the simplifications. So in a very simple model, he found that the normal stresses in the shear flow here, this is tau 11, we have to talk about notation, but this is basically the tension along the lines here in the material elements flowing downstream. And that's the shear stress. And this value now, this ratio taken at the wall, where it's maximum shear stress, maximum normal stress. So that stress level gives the value of the swelling afterwards. The depends is not very strong. It's a 1/6 root here. Well, here's a square, and then so it's about 1/3 root in this case. Okay, what else do we have? We have interesting slip phenomena in capillaries. Oh no! Let me talk about here one more. If the extradate is round, then you just see a change in diameter. But if you have an extradate, if you have to produce an extradate which is square, which has some fantastic shape, then the swelling will ruin your plants because the swelling is not symmetric, and it changes everything. Now here is a set of data by Reutemeyer in 68. He took a capillary which is square because he wanted to extrude something of square shape. But before that, he had a little section which is either a star, very extreme star here, or a little less extreme star, or which is a round cross-section. So somehow there's memory to this upstream round cross-section or star or whatever. So, and then he made his die of different length. And he found that when he extruded from this type of die, perfectly legal, round die, and then he has a square for quite a while, he gets those balloon-shaped extrudates. They certainly don't qualify for being square. But then by having a pre-section which is helping the corner here, he gets more material into the corner, and it's kind of okay. This, with a little help, they might be okay. But here he overdid it. He put in very sharp corners, and you can see there's an overcompensation. So just making those profiles is very, very tricky, and it's due to the shrinking and to the swelling of the material when it leaves the die. Complicated geometry, hard to predict. Okay, I see my time is running out here. I have, a few other, maybe slipping I will discuss next time. That's an interesting phenomenon. But basically today I wanted to describe a few phenomena in non-Newtonian liquids, in elastic liquids, which are different from phenomena you are used to see in fluid mechanics, in classical fluid mechanics or classical solid mechanics. And those phenomena mostly originate from the elasticity of the material. And you can see that for quantifying elasticity, we are talking about a time constant of the material, time the material needs for relaxation. And elastic experiments always require a time scale short enough so that the material memorizes, has a memory, hasn't forgotten the history which would give rise to those elastic effects. Or if you have a material which has a relaxation time which is short enough compared to the processing time, or if you process it at long times, like a steady load on my bouncing putty, then it flows and you don't see any elastic phenomena. So in that order, we have to study the polymeric material. And that's also where rheometry will be most interesting, most characteristic for the polymeric material. Well, thank you. That's it.